Welcome to the second lecture of this module. In this lecture, we will be looking at power electronics and how it plays a role in renewable energy sector. The objectives of this lecture are 1. To explain why power conversion is required for the grid integration of renewables. 2. To explain how typical power electronic converters work. And 3. What the basic functions of a power electronic converter are. Generation of renewables highly depends on the weather condition and location, which means renewables cannot always match the local power demand. Therefore, it is preferred to integrate renewables into the grid so the generated power can be sent to any place that has a power demand. However, the renewables cannot be or is not appropriate to be directly connected to the grid. For instance, the PV panels have a DC output, which does not match the means as an AC voltage source. Wind generator outputs alternating current, but the magnitude and the frequency change according to the wind speed, which again does not match the means that has a fixed magnitude and frequency. Connecting renewables directly to the grid leads to grid failures and blackouts. Power electronics are then applied as an interface between the power generators of the renewables and the means for power conversion. In general, the power electronics can do 4 types of power conversion, including DC to AC, for instance, PV power inverter, AC to AC, for instance, wind power inverter, AC to DC, and DC to DC. This will protect the grid by adjusting the power to match the grid. Let us see how a simple power electronic converter works. The operation principle of power electronic converter is briefly elaborated by this topology, called buck converter. It is composed of one switch and a diode for freewheeling, followed by a low-pass filter formed by an inductor and a capacitor. The switch, essentially a power semiconductor, operates in only 2 states, on and off. On state is like short circuit with a little voltage drop across the switch, and off state is like open circuit. So, by tuning the switch on and off, the voltage after the switch is chopped between VDC and 0 at a frequency called switching frequency. The switching frequency voltage noise is then filtered out by the low-pass filter, so the load can only see a DC voltage. The DC voltage equals to the input voltage times the duty cycle of the pulsating voltage. The duty cycle is dominated by the comparison between a reference signal VC and the carrier in modulator. The voltage on the load eventually can be controlled by tuning the reference signal VC, and this is how a typical power DC-DC converter works. Similarly, by applying 2 switches in one leg, a bipolar pulsating voltage can be generated. For example, if the reference signal is a sine wave, a sinusoidal pulsating voltage can be generated at the output of the converter. And this is how a DC-AC inverter operates. Back to renewables, the mainstream wind power generators can be categorized into 2 types. DFIG, which is short of doubly fed induction generator, and PMSG, which is short of permanent magnet synchronous generator. In DFIG, the stator of the induction generator is directly connected to the grid via a transformer. The rotor winding is connected to the grid via an AC-DC-AC converter. In this way, the rotor frequency is not fixed by the grid voltage. Instead, it can be varied according to the wind speed to achieve maximum power point tracking. In PMSG, the stator is connected to the grid via an AC-DC-AC converter, so the generator again has a variable frequency with MPPT capability. But with such a configuration, the power converter needs to process the full-scale power of the generator, which was not possible in the past but is becoming the mainstream nowadays due to the development and cost reduction of power electronics. PV panels usually have a voltage much lower than the grid, so a step-up DC-DC converter, also named boost, is applied, first to create a relatively high DC voltage, then a DC-AC converter is followed to create an AC voltage for grid connection. Power conversion between AC and DC is the basic function of power electronics. As a controllable component, power electronics in renewables can do much more. Hence, controllability and flexibility of power electronics are its important aspects. To summarize, on generator side, the major function is maximum power point tracking by controlling the speed of a generator or output voltage of the PV panels. On grid side, power electronics enable active and reactive power control, harmonic current mitigation, low voltage ride-through, and other ancillary services. To recap, power electronics are required to smoothly integrate renewable power output with the grid and to mitigate the variations that renewable energy possesses. We saw how a typical power electronic converter works, with a simple buck converter serving as an example for DC-DC power converter and a double switch circuit for the DC-AC inverter. We saw the typical applications of power electronics in wind turbines and PV panels. Finally, the basic functions and strengths of a power electronic converter were briefly discussed.